My name is Andreas Fertig. I work as an independent trainer and consultant for C++, and occasionally I also give talks like today. And today is very special because I'm also the creator of C++ Insights, and that's the topic of today. C++ Insights, how stuff works. C++ 20 and more, because we now have C++ 20. I just read a tweet that LLVM's libc++ now has full concept support. So we're really getting to full C++ 20 compiler and library very soonish. But before I start talking about C++, let me talk a little bit about my name, more precise, my last name. My last name is Fertig. It's an adjective in German. And you can translate it in English with finish, ready, complete, or completed. Being an adjective isn't that easy because an adjective in German is spelled with a lower first letter, while my name is, of course, spelled with a capital first letter. So I have a constant disagreement with my spell checker who is right or who isn't. And this leads to trouble. Sometimes there is a Fertig with a capital F where it shouldn't be, and other times I write my own name with a small capital F. So things like that happen. The name itself, it's great. I really like it. One of my friends, very, very long time back, came up with the idea if what would be if my last name would be trademarked. And of course, if I would be the owner of this trademark, so I would get, let's say, 1 cent per mentioning of Fertig. And because it's a frequent word in German, I probably would be very rich, and it would be a nice world, at least for me, and I can give away money and spend it on people who need it more than me. But I'm not there. I even, had 30 years with my own name until I learned that I mispronounce it. I say Fertig. If I do not watch really carefully, I say Fertig. And turns out this is more the dialect tongue speaking here, because in proper German it's called Fertig with a ch sound at the end. Usually nobody complains, everybody gets it, but it's a little sad that such a typical German word, which also is my last name, I'm unable to pronounce correctly. So that being said, I'm also the same person who will now tell you some things about C++, which is not in my name. So I hope I do better justice to C++ than to my own last name. So what's C++ Insights? C++ Insights shows you what's going on with your C++ code. So on the corner bottom, the right half of the slide, you can see a very small screenshot. We will see live demos later. But essentially it's inspired by Matt Gottwald's Compiler Explorer. You put in your source code on the left and you get out your source code on the right. I still think it's a brilliant idea, worth millions of dollars, of course. Getting C++ code from C++ code, hey, there's a market for that, right? The difference is the output is enriched with all the things the compiler does for us to make our code compile. And we will see a couple of these examples. So this helps you to make invisible things visible. I like the language as it is, so the implicit things which are there are usually very good. They make it easier for me to write code because I have to write less code. But of course, sometimes even I wonder what's going on there. And I found that C++ Insights is a very nice resource to peek behind the scenes and either get reminded why things as they are or learn why they are working as they are doing. The tool is free, it's open source, it's on GitHub. You can head over there and clone your own version. You can compile a command line version, so you can run it in your build process. I don't know anyone who does this. It's probably too much output anyway, but you can run it on your command line. You can also set up your own instance, so you don't have to put your company source code in the public version of C++ Insights. What I aim for is to create valid code. My imagination is really wonderful. So having me make up code that is the transformation of your C++ code, that's probably a thing that could be too much misleading. So I try to create valid code, and I do this by testing the result from a C++ insights transformation with either Clang or GCC or recently even MSVC, and compile this again to see whether at least it compiles. I could do a bit of a better job in even ensuring that the result is the same, but I'm not there yet. And this compiling helps for certain cases to catch bugs and so on. So this is the broad overview about the tool. So let's dive a little bit into the motivation. This here is an example. This is, well, you can say even C code. There's not so much C++ in it, but let's say it's C++ code. What's going on there? So the quick question I usually ask the audience is, what is the obvious output of the printf? I mean, let's walk through it. I have two variables in my function use, A and B. A is set to 1, B is set to 6,500, 530,000. So, of course, if we are asking with this max function, which tries to figure out which of the two values is the greater one, guess who wins? B, of course. B is way greater than A, correct? Well, the next question would be, how many implicit conversions are there? So what's happening behind the scenes? Why is this thing working? And this is where C++ Insights comes in. So ask yourself for a moment, how many implicit conversions do you see? How many are there? So this C++ Insights live now. As I said, you put in your source code on the left and you get the transformation out on the right. So if I transform this, and it takes a while because my laptop is busy with screen sharing, but at some point it should do it. So, all right, this is what C++ Insights shows you. There are a couple of implicit conversions going on, 4 to be correct in this view. So we have one here which casts my B, which is in fact an unsigned short, to its short, to be able to call max, because max expects 2 shorts. It's nice from the language that it does that for us, but sometimes it would probably be better if it wouldn't compile, because it creates trouble. So inside of max, I do have 2 other casts. They cast my A and B variables up to integers. So they do an integer promotion. Why? Because the standard says that we can only compare integers or greater, but not short or chars with each other. Well, all right so far. And then we get another implicit conversion from the result of max, because max here returns a short, but our printf function takes ints because they're put on the stack. So 4 implicit casts, and if I manage to run this example now in Compile Explorer, then we will see that in fact, in this case, 1 is so much larger than 6,500, 530, at least if we manage to get good bolt running here. I didn't prepare this part, but you can think about questions and you can think about what the result is. Darn. Let's try it simple. The only thing I didn't prepare in advance, and of course that one fails, We'll see what else fails. All right, let's not spend too much time on that. So the answer is that my printf call here will tell us that 1 in fact is greater than 6530, simply because all these implicit conversions. Because my unsigned short, when it gets promoted to a short or converted to a signed short, to be precise, then this number becomes a very small negative number, which is then greater than 1. If you like to see what's totally going on here, you can turn on this option, show all implicit casts. I usually have that one off for classes because it's simply too much traffic. And that transformation happens, then we can see way more casts. So 1 is of course an integer. It's not a short. So there's an implicit conversion converting my integer to a short. And 530 of course is once again an integer and not a short. So it gets converted to an unsigned short. So there are a couple of things happening to our source code which we know, which we learned over the time, or which we are not aware of. And C++ Insights helps us making these things visible. C++ Insights is a Clang-based tool. It uses the very terrific AST of Clang, which makes things so much easier for me because parsing C++ is a total nightmare. So it uses Clang AST, so that way it's way more than a preprocessor. Okay, it's not just such a simple regex thing. No, it has a full C++ parser front end beneath it, and it uses the output from that. I use the official builds of Clang, usually the latest version, but I'm a little bit behind because I'm waiting for the next revision coming up from Clang, hopefully the next days or weeks. So it's not using current, so you may notice that not all of the latest features are available, especially if you're looking in the new C++ 20 stuff. The reason for that is really simple. I like to have a way to find bugs and issues, and if you're reporting an issue, for example, with an unstable current release of Clang, then I may have a harder time tracking down what the real issue is, and maybe it disappears because it was inside Clang and it was fixed then. Because it uses the Clang ASTs, if you're looking at what a compiler does, we can roughly separate it in the back end and in the front end. So the front end parses your source code and creates the AST and then hands that to the back end. And the back end does optimizations and the actual transformation to a binary. So it produces the assembly or even beneath the binary output. The front end does very little optimizations, at least in the case of Clangs, as far as I know. So it does some things like constant folding. So if it comes across 3 plus 4, then of course it sets in 7 for that. But all other optimizations, they happen later in the back end. So passing -o something to C++ Insights has absolutely no effect. That's the reason why on the website you will not find such an option, because the optimizations, the real optimizations, they happen later. And okay, one side note, not all statements are currently matched. I recently stumbled over a recovery statement, which Clang injects if you forget a semicolon, something like this. But this is probably not a statement you're looking for. But if you find something that's currently unsupported, feel free to tell me. I try to implement everything that's usually used, but maybe I overlooked something. There are a few limitations I like to mention at this point. And one of them, or the biggest one of them, is templates. Creating code for templates that actually compiles and is in some definition at least correct is very hard. And to make this a bit easier for me, I decided to have this insights use template if def here. And if I do this transformation, and I should have opened this in Compiler Explorer. So let's see. I can make it this time. So let's start with this. This is the sample from the slides. And if I do the transformation here, and we are waiting a little bit. It's the payment I have to do for this virtual thing. So then we can see, of course, what C++ Insights does here, because my function func is instantiated with the demo type from the class demo. Then I get an instantiation for func with demo. So looks like a specialization for this. This is how the compiler stances out the specialization or instantiation, to be precise, for templates for us, for this primary template func here. So this is the result. And if I take this and punch it into Compiler Explorer and be fair and enable my guarding define here, then we will see, oh, it doesn't compile anymore. And what the compiler says is that the demo isn't declared at this point. So the code will compile once I move the definition of demo before template specialization or instantiation. And this is why I have this, this define here to prevent a couple of compilation errors, because it's very hard to know where to place this specialization. Currently, I took the easy approach and I always put it directly beneath the primary template. I can put it on beneath this demo class here in this simple case, but in reality, things are more complicated. So this is where I'm stick right now. And if you have a great idea for a patch, then feel free to tell me. Otherwise, now you know why this, if the template guard is here, this just helps me to make it easier. So I said Clang, AST, C++ Insights is AST based. So what's an AST? That's an AST. And question would be, what does this AST do? And a fair answer would be, I don't know, because this AST is so much shortened, I cannot tell you. If I create this AST on my local machine, then it generates a whole bunch of pages of output. And at the very bottom line, you see what it's really doing. It's the most popular program. It's a Hello World program, saying hello C++ here in the last line of the output. So this is essentially the code behind it, nothing more. On my machine, it creates approximately 190,000 lines of output. This piece of code, okay? This is all the stuff the compiler does for us. It includes headers, it instantiates templates, even if we are not directly using them. And the AST itself may be a little bit bloated here because it carries a lot of information, but this is the information the compiler has to maintain it at some point at least. So there's a lot of work going on behind the scenes, and at the top you see the view from C++ Insights. All I'm doing is taking this AST and converting it back to C++ code. And in a lot of cases, this is easy, and in some, it isn't. This is another example where I can use C++ Insights. So let's say I have this class template called cooled template. It has two data members, msize and mdata, and it has two constructors. one that takes a const t star data and a size t, and the other one is once again templated. It's a method template or template constructor template, and it takes a reference to an array of size n. Now below in line number 18, I instantiate the class or initialize a class of type cool template jar. I name it CT and then initialize it with buffer. Buffer is just a jar array of size 5. Which of the two constructors is picked? Line number 7 or line number 10? Here the answer is probably relatively easy depending on your knowledge about C++ and sites, or on C++. But let's see what C++ and sites can do here. It's not a primary use of C++ in sites. I discovered this when I did work on something else. So this is the code from the slides. And if I do the transformation with, remove this for later. Let's do this again. So if I do the transformation, then we can see 2 things. So first of all, we see here our primary template definition. Once again, it's the same that we created. And here below, we see, like with the function template before, the instantiation of a class template, okay, or specialization, depending on how you like to see it. Okay, it's no big secret. Of course, all t's are replaced with jar. The important part is now the code here. I create a cool template of type jar with buffer. And the question was, which of the two constructors is called? And C++ Insights in this easy case can give you the answer because it's the one that gets instantiated. Okay? Here, this one has an instantiation. It's the one taking a jar array. The other one, the one here, goes without an implementation in this class template instantiation. If I add this other object of cool template jar here, then we can see that now both constructors have an implementation or specialization implementation in this class template specialization. So this is how you can figure out which constructor gets called. If you can break down your example enough, then C++ Insights can help you see through here. I once had a case where we really did this with production code, and it helped us figuring out what's going wrong, because we knew that something wrong, but we didn't know what exactly. And after getting it down and putting it into C++ Insights, we finally saw, oh yeah, that's the wrong constructor being called here. So it can be helpful in such cases. When I started developing C++ Insights, I stumbled over things like this. Yeah, it's a function here which has a default parameter. And line number 1, int x equals 23. I think that's not necessarily new to you. And then, of course, we can call it in line number 5 and simply saying func parents, and that's it. But how does this work? I never actually really cared because it worked, so it's fair to say I don't care. And C++ Insights gives us the answer, and that answer is pretty simple. The compiler simply puts in 23 in every location where we call this function without passing a parameter. So the function declaration at the top at the right, that looks very much like we would write it without the default parameter. So the default parameter simply gets removed from the function when the compiler parses it, and only the value of the default parameter gets inserted in all the places where it needs to. So sometimes things are really simple, at least if you're not a compiler developer and have to care about this, but you can simply use it and see how it's working. Let's switch to something else. Default member initializers in C++11 and later. So I have this class here called Init. It has 3 data members in line 7 to 9, I, V, and S. I gets initialized with 0, V with 2,3, and my std_string with hello. All 3 are in-class or default member initializers. And then if you look at the default constructor in line number 3 to 5, then you can see that I gets initialized to 9 there. And now it's an int, but so it doesn't really matter, but sometimes in my classes I get a question, do we now have 2 initializations? So how is this default member initializer or in-class member initializer working? Because if it's not an int, if it's something more expensive like the std_string or my std_vector, which gets initialized 2 times, then this feature may not be what I'm looking for because it's simply too expensive. And here once again, C++ Insights can help you to see through. What's happening here is basically syntactic sugar from the compiler. As before with the default parameter, the in-class member initializers, as we see them in line number 10 to 12, the compiler just takes them out. So these members are like regular members before C++11, and it puts their values in all the places where we need them in our constructors where they need to be initialized. So we see this on the right in line number 9 to 11. I have my variable I, my variable V and S. And if you're looking at them, then we first see I is initialized to 9. Only once. There is no 0, it's simply the 9, because if we are specifying a value in the constructor, that one wins over the one as the default initializer. Then my vector V, here it gets initialized with 2, 3, and 4, exactly what we asked for. And my std_string, of course, gets initialized with hello. Sorry for all the noise you're seeing here. This is what's behind the std_string, but that's not part of the talk today. So this is syntactic sugar we are looking at. So the compiler simply moves things around for us, and after that movement, things look like they did in C++98. And once I add a second constructor here, let's say I have one that takes an int, and I simply do nothing, and I do the transformation, then of course I get the benefit of the in-class member initializers, and this constructor uses the default values that I provided for all the members below. So this one now here has the I equals 0 because I didn't specify an override for I here, and all the others have the same. So the value we are getting out of this is we have no uninitialized data members anymore because they get initialized. We may not be happy with the value, well, that's a different question, but it's the value we set, it's the default. What can C++ Insights show you other? It can help you with the following. Do you know or do you remember what constexpr meant in C++11 for a member function? Assume you have the code like presented here. I have a struct, I call it cpp11, and it has one member function with the name fun. It simply returns true here because I don't want to put any logic in here. It returns bool, and it's a constexpr method, of course. So, is there anything special? Is there anything going on that we may not expect? This is the transformation of C++ Insights. And if you look at it close enough, then you will see that there is a const there. There's an inline keyword here as well, because constexpr methods are implicitly inline. But this const, this is very interesting because this member function here is not marked as const, but it gets marked as const once we add const export to it. And the compiler, in this case Clang here, already gives me an answer to that. It tells me that in C++11 all non-static const export functions are implicitly marked const, but once I switch the standard, say to C++14, that goes away. And this is a breaking change, because in C++11 there were implicitly const export, and in C++14 they are not. And the reason for this is very simple, because you may like to have different functions which do very rubbish things here, but now we can provide a const overload for my member function. In C++11, this wasn't possible. So this was why this breaking change was applied, despite it was breaking. Let's talk a little bit about lambdas now, shall we? More specific captures of lambdas. Assume I have this class test here, and it has an int member in line number 2. It's called A. I'm very easy with the names today. And then there is a constructor taking one argument, once again an integer named x, and here in line number 5, A gets initialized with x. And then in line number 7, in the body of the constructor, I create a lambda L1, and this gives me the result of A plus 2. So whatever A got initialized with, add 2 to it and give it back to me. And this is initialized, or the lambda is capturing by copy. Now in line number 9, I use a printf, and I invoke the lambda to print out its value. And then, because I can, in line number 11, I increment A by 1. And just because I'm curious, I'm printing out the result of L1 once again. So all L1 does is it adds 2 to A, but it's capturing by copy in line number 7, so way before I increment it once again. And the question is, what's the output of this program? 3, 2, 1. The output is 4 and 5. So it was called in line number 19, initially with 2, so test was constructed with the value 2. So of course, 2 plus 2 is 4, everybody knows that. So my lambda should return 4 in all cases, but it doesn't. After I incremented A, I see the effect. Now it's no longer 4, it's 5. But I copied A into the lambda, correct? So that's at least what the syntax says. But that's not true. What I'm doing here is I'm capturing the this pointer. And this is where C++ Insights comes in. But this is the code from the slide. Here I'm capturing by copy my lambda. I'm adding 2 plus A. And here's the transformation. So first of all, this is our lambda. Okay, a lambda internally is modeled as a struct or class. The name here is something I have to make up because the compiler doesn't have a name. Another name for lambdas is anonymous function, so they don't have a name. And the class type is made up by the compiler, so the compiler doesn't need to bother about giving it a name. But for my goal to make compiling code, I have to do this. Now, what's special here? A lambda has a call operator. This, once again, is something we can write ourselves. And in this call operator, we find the contents of our Lambda. So this is our return a plus 2 here. With one exception. Here is such a dash dash or underline this. And this comes from here. And the reason is that because I use this inside of a class, my Lambda, and I say that it should copy all the captures, I in fact copy the this pointer. I'm capturing the this pointer of my class test here. So this is why my Lambda has a data member test pointer, and I have to name it somehow. So this name is also made up by myself and not by the compiler. So this is a reference to the this, or it's pointing to the this pointer of test. And other than that, my Lambda, of course, has a constructor, which is technically not totally correct because the compiler can play nice tricks here and saves us the constructor in reality. So this is what's happening here if I capture by copy. And this is often not what we really want, despite that we want to capture by copy. So what we can do is we can change it. We can say that we capture star this. This is a C++ 17 feature. And the star this you can read as that we like to capture a dereferenced version of this. So practically we like to copy the contents of this. And if you're looking at this, then we can see that the compiler now captures or parses star this to the constructor of our Lambda, and that the Lambda internally no longer stores a pointer, but now it stores a this object or a test object, and the rest is the same. But that way, if we are going back to the slides, because I prepared the output there, that way our result now is 2 times 4, because incrementing a in line number 11 has no longer an effect on that, because I'm no longer capturing this pointer as a pointer, I'm now capturing the object itself. This helps you around this issue which you may come across. But what does this mean for the size of your Lambda? So I worked for a long time in embedded, and I did care and still do care about the resulting size or the size of an object in my code, because the either RAM or ROM was very limited. So say I have a variation of my class test. It's still there like before. It starts with one data member int a, but it now has another data member int b. And my constructor is still the same, takes an integer, and I got rid of all the printfs here. I'm simply capturing in the body of the constructor a Lambda, calling it L2, and it captures star this, and it does the same as before, it returns a plus 2. So obviously all I want, or all I'm interested in this Lambda is a. If I now look at this in C++ inside, then we see what we saw before. This is the transformation of my star this. And here, I'm still capturing the whole class by copy, the object by copy. This is what I asked for here. But before, it captured only a, or it copied only a, because the class only had one data member a, but now it has 2. So in other speak, the memory consumption doubled. Okay, it's just an integer, but it doubled. This is not really what you want to do in a lot of places here in your code if you're capturing and only interested in one variable, because the thing you're capturing may be bigger, so the class, because it may have some string in it, some vector which allocates a lot of memory. So the thing you can do in C++ now is you can use init captures. They came in, I guess, with C++ 14. And the syntax is interesting. I can here at this point say a equals a. And by that, what the Lambda captures now is a variable named a. And because this is not really good to know what's going on, I'll rename this to b, which you can do as well. Oh no, I have b above, so let's name this c. The clear indication what's going on. So here, once again, we see the body of the call operator, and that one now says c plus 2, because it's the same I've written here. And this is my init capture here. And now we can see that the data member of my Lambda is named c, and it gets initialized with an integer with this a. So with a from the class test. And that way you can reduce or control the consumption, the memory consumption of your Lambda by being specific. If you are inside a class, then be aware that it captures this pointer by default, but you can restrict it and say that you want to have only this single data member or other data members as well captured, as opposed to capturing it either as a pointer, which is often not that good, or capturing the entire class, which comes with other drawbacks, because you now increased your memory consumption. So Lambdas are an interesting thing. With C++14, they got improved a little bit. We got generic Lambdas there. This is the auto syntax you're seeing here. And what I'm doing here is I have a Lambda which then gets assigned to a variable named max. So inside of this Lambda, I'm trying to figure out which of the two parameters is greater than the other, so x or epsilon, and that one is returned. There is a std_max function in your standard library, and you should refer to that. I'm just trying to make a point here, and not saying that you should implement it yourself. So this is with a generic Lambda. This is great because it gives me the flexibility to say, okay, this is what this thing does, and I am open to use it with any type. This allows me in line number 7, for example, to call max with 2,3. This is great. It also allows me to call in line number 8 max with 2,3.0. Oh, for me, this is not so great. This is not what I want, because remember from the beginning, implicit conversions. I'm mixing types here. That thing compiles, but what does it return? Is it the right type it returns? And even if it is, how many conversions do I get in between? And is there a loss of precision somewhere? So this is nothing I want to compile. And let's peek behind the scenes what's going on here first. So this is the transformation of my code. We once again see here, this is my Lambda. This is the call operator of the Lambda. But this time, we are looking at a method template. Okay, it's no longer a simple call operator, it's a method template. The compiler creates a method template out of this for us, and it gives it 2 class or type parameters, which you can see the name also comes from the compiler, so it's just generated because we cannot name the type here. We said it's auto. These are my 2 parameters, x and epsilon, and this is the body. And now here we can see this method operator gets instantiated once with 2 integers, and the second one below here with an int and a double, because this is the second case that I don't want. And now we can see here, oh yeah, there's a static cast, so we are promoting everything to double, and we are returning a double. Well, maybe this is what you want. It's certainly not what I want, not automatically at least. This is the implicit conversion I don't like. So what can we do? At least if we agree that this shouldn't compile. You may disagree with that, that's fine. There are cases where it's okay if it works. This is C++20. In C++20, we got another improvement of templates, of lambdas called lambdas with the template head or templated lambdas. And you can see it in line number 3 on the slide. What they bring us is the angled brackets. After the capture list, before the parameter list of a lambda, we can, in angled brackets, now write our type name or our non-type template parameters there. So between these angled brackets, we can do the regular things we can do for functions or function templates, to be precise. Sorry. So, and if you look at this in C++ insights, there we can see, oh, there's no real difference here. Our call operator is still a method template. The only difference is that this time we named this parameter and we said it's a type name. So type name t. And that allowed us to refer to this t for x and for epsilon. And that way, both parameters now need to have the same type. And because there are no implicit conversions when it comes to templates in this case, this code piece will now no longer compile. So Clang tells me there is no candidate because it has conflicts when deducing the types for t, int versus double. So this case no longer compiles, which is exactly what I want. This is great because lambdas with a template head allow me the flexibility here to still say I'm open to any type, but please make a and x and epsilon be of the same type. This is the key here. And this is what lambdas with a template head give us in C++20. What else do we have? Well, range-based for statements. This is an example where range-based for statement does something different than you like it to do. We have a struct keeper here, and it stores or it contains a data member called data. It's a stored vector of int and initialized with 2, 3, and 4. And then there is some kind of an access function called items, which returns a reference to this data member. I try to keep it on a slide, so in usual code, assume that the data would be private and all the items would be accessible. So far, that's okay. Then I have a function called get, which returns a keeper object. And because that's slide code, this simply returns a new object of keeper. That's also all right. And then below in main, in line number 14, I have a range-based for loop now. And what the intention of this range-based for loop at least is it creates a new variable it's a reference called item, and this should get initialized for every item in my keeper object, and then I print it out. So I have here colon get.items. So I first create a keeper object with get, and then on that I call items to get a reference to the stored vector, and then I can iterate over all the elements. And I see them, you see out to print them out. If you look at what's happening there in C++ insights, we can see the following. So you once again see a little bit of the standard library going on here. This is the GCC, that's the GCC implementation. So libstd C++, this iterator pair here. So, but we have this range-based for loop here. Let's start there. A range-based for loop boils down to a regular for loop. The compiler creates a new scope for us. It opens a scope, and it creates 3 variables: range, begin, and end. Compiler here, in this case Clang, gave it a postfix of 1 here, but that doesn't matter. And then range gets initialized with the result of get.items. And this is type stood vector, so it's the same type. But this is a reference, okay? And it's not a const reference. That's the problem here. Because get returns as a temporary object, because it returns an object. At this point, it's a temporary object. And then we are calling .items on this temporary object, which would be fine. But now we are binding this result to a non-const reference. And by that, the result here doesn't get lifetime extension. That means range is now used to call range begin and range end on it. So the begin and the end of the vector, and then inside of the for loop, here, this is the internals of the range-based for loop. Now it's a regular for loop. Here I have an operator equals that compares whether begin and end are equal. And here I have a call to operator plus plus to increment the iterator after each loop iteration. And now here I'm creating my requested variable item, which is a reference. And here we can see the call to begin dot operator star to dereference the iterator, and then it's printed out. But after this line here, my temporary is gone. So once we hit the semicolon, the temporary gets destroyed. So everything we do with that range 1 after it, that's just undefined behavior. You may be lucky and it works. I'm not sure if it's really luck then, because it shouldn't work. But because it's still on the stack, sometimes it may work. As I said, I'm not considering this luck, but it may help you. Chasing that bug is really not fun. What can we do? We can use C++20. The code is roughly the same, except if you're looking at the for loop, a range-based for loop. In C++20, we have range-based for statements with initializers. This allowing us to write the same as for regular for loop. We can provide an initializer and after that have our usual iteration statement. So here on line number 14, you see the initializer. There I say, I create a new variable called items and I initialize it with the result of get. And now in line number 15, I'm iterating over the result of items.items. Poorly chosen name, I admit that. But now I don't have a temporary, no longer, because items in line number 14, that now is the thing that captures it correctly. And if I do the transformation here, then we can see the secrets behind this action. It's also not quite surprising or not so difficult. It's just, once again, syntactic sugar. C++ Insights just takes a moment. Sorry, my request failed. What's that? So I hope you write down all your questions, because at least I give you the time for that. What's wrong now? But now, come on. Yes. All right. What this does is, inside this scope, the compiler creates for us for a range-based for loop, it simply puts the variable declaration we are requesting in front of that as the first line, and after that, the same thing as before continues. We have our range variable, which now calls items.items. And with that little, I'm not sure if trick is the right word for it, but with that approach, you avoid iterating over a no longer existing temporary, and by that using UB. Nikolai Yositis tries to fix this in a much better way by extending the lifetime of this statement without having to play the tricks with the initializer here. That would be nice. Maybe we are getting this for 23, but so far, watch out for this. This can cause real nasty problems. And of course, what you can also do is, it's not a use case. You can now declare, just the primary use case, variables on a very narrow scope in a range-based for loop. So if you need a variable in a range-based for loop only there, like here with my index variable, then we can declare it now in the initializer part of a range-based for loop. So it's not necessarily just to avoid this temporary situation. We can also make use of it for otherwise working code by narrowing the scope down, which is also beneficial. Well, we're talking about C++ 20. We have spaceships in C++ 20 now. You probably heard of that. We have the spaceship or three-way comparison operator. And the promise of this operator is we have to write our comparisons only once, so only one comparison function in the name of operator spaceship, and the compiler generates all the other methods for us. And that's really great. You have an example here below. How does this look? I have a struct spaceship which has a single data member X, and it has there in line number 4 and 5 the spaceship operator. And C++ 20 is really great. I can say here stood weak ordering, which is a new type from the compare header, which is also new, but I could also say auto. And then I can default this spaceship operator. Okay, I don't have necessarily to provide the implementation of this operator. It's like a default constructor, which we can default since C++ 14. And in line number 10 and 11, I'm creating two spaceship, the Enterprise and the Millennium Falcon. And because I couldn't decide which one is the better one, I assigned 2 to both of them. And then in line number 13, I'm comparing whether Enterprise is less or equal to Millennium Falcon. Okay, this line 13 requires a tremendous amount of code pre-C++ 20. So let's look what's happening here. So above, we can see a couple of other things. So I haven't declared this operator const expr, but a compiler chose to do it because it sees that it can't be. So this is another effect we are getting here from the spaceship operator. If we default it, the compiler marks it const expr. And for all those who care, it marks it also no except. So these are things C++ Insights shows you. We see also a second operator, which we didn't type or request. This is operator equals. So if the class is as simple as this, if we are requesting the spaceship operator, we also get the equality operator. And now below here, in line number 16, we see the comparison. And now we can see that the compiler invokes operator less than or equal on the result of enterprise.operator spaceship Millennium Falcon. So it calls the spaceship operator of my enterprise class, object, it passes in the Millennium Falcon, and now it uses operator less than or equal to compare the result from here to run from the standard library. So it's a special type from the standard library which we shouldn't care about. And the value here, as far as I know, is implementation specific. Maybe that's why it's named unspec 0 here. But this is how it works. The compiler uses the global less than or equal operator and compares the result of spaceship to a known value, because spaceship, practically, depending on how you're seeing it, returns 1, 0, and -1. So we implemented something like this in the past. This is spaceship. This is what people often talk about when it comes to the spaceship operator. There's more. Before we got the equality operator for free. What if we simply provide it? We can do this. We can then provide our own implementation, which does the same thing as the compiler would have done. And in line number 13, instead of comparing for greater than or equal, I'm now comparing for equality. Is my enterprise equal to 2? And those of you who dealt a lot with comparisons in the past before C++20 may know how much code it means to make this work. Because this version is typically the easy one. You can refer to this operator in the class. But if we flip or switch the two variables, if we say 2 equals enterprise, then we are in friends land. Typically, then we declare friend operator taking two parameters, a spaceship and an int, and the same operator once again the other way around, which takes an int and a spaceship to make both versions work. That's what we talk about when we say consistent comparisons, because we like to be able to flip sides and the comparison should still work. So how does this work? And this is an interesting additional feature we get in C++20. Notice that I provided only the usually simple case, the member function operator equals. And in this case, of course, the compiler says it calls operator equals with 2 on my enterprise object. Now, if I flip this around, what's happening there? This is the interesting question. Now watch out carefully for the difference. We are taking a bit of time here. Well, the transformation is done. Do you see a difference? I guess not, because there is none. The statement is the same. And this is due to a new ability of the compiler in C++20 called operator rewrites. The compiler is able to switch the operands for us. So we do no longer have to provide 2 equality operators here, or friend version, because the compiler is able to transform the statement we have on the left into the one of the right, because it looks up, finds this one equality operator, and then in its lookup table it finds out this is one way to go, and it's the only one, so it simply flips the arguments and make this code work. This spares a tremendous amount of code if you're writing classes with comparison operators. So what can C++ Insights do for you? And the answer is, I don't know. But I can share my experience with you. You've seen the tool in action, maybe you knew it before. So the most valuable thing, and I was inspired by Matt Godbolt's Compiler Explorer by that, is seeing, making things visible. This is so valuable. So things you may know in C++, but you just don't expect to be there, or you are not aware of in some moment, C++ Insights can help you see them again and make you aware that they are happening there. This is very, very helpful. In several classes I taught using C++ insights, as well as Botgold's Compiler Explorer, of course, they tend to be way more interactive than classes I taught before I used C++ insights. Attendees tend to start asking broader questions about a feature, so they're really trying to apply it and to work with it, and applying certain other constructs to it, and start wondering how this works and how this turns out. It's not always usually down to the last byte or to the last nanosecond something will end up. It's the decomposition and how things work in general, and to apply them. So I think they tend to learn more, or at least they get a really good understanding of what they just learned. And we saw it with the C++11 example. C++ Insights can help you to see the little differences, and sometimes it can help you to settle different opinions by visualizing what the compiler does. It's only Clang. There's no GCC version of it, so you can only see what Clang does or would do. And you may still disagree and say that's not standard conform, but it helped in a couple of occasions to say, okay, this is what the compiler does. Here you can see it. We are once again at the seeing. And like our IDEs, whatever they may be, I showed you that C++ Insights can visualize template instantiations. And seeing them, once again, often helps. But I showed you the example, the absence of something, that can also be valuable. If you know that only this constructor gets instantiated, or this method template, but not the other one, or you see a bizarre, for your expectations at least, combination of types instantiation a certain function template, then this made a clue to why is the code not doing what I expect it to do or what I want it to do. So these are my insights of what C++ Insights can do for you. Feel free to share yours if you already have some. So the project, you can support it. New features, fixes, even in the documentation, are very welcome. You can head over to GitHub and download or clone the repo there, and try to send me a PR of the latest, coolest feature. If you have a little bit of money to spare, then you can support me on Patreon, like you also can support Meeting C++ there. And if you like to get something you can wear back for your money, then you can try the Spreadshirt shop of C++ Insights. And it's always, of course, all the time okay to simply send me an email and say thank you. I still get these occasionally, and at this point I like to thank all the people who write me these letters or emails. I appreciate the time you take, and I will keep up with the project and bring it forward. And at this point, I told you about my name in the beginning. Do you remember this? I recently had, for a training advertisement, come up with a short URL. And my whole name, andreasfertig.info, which is my regular domain name, that's awfully long. Especially if you have to put your also awfully long class name behind it, your advertising. So I came up with a new domain for things like that. And now we can use fertig.to-subscribe. Isn't that cool, to subscribe to my newsletter? Ready to subscribe? Ready was already picked, and it's not my name. So fertig.to/subscribe. You can head over there, subscribe for my newsletter, get a concept cheat sheet, and stay in touch with my latest news, which I will share with you more about the domain. So at this point, all I have to say is I'm looking forward to your questions, and I hope you had fun. I am Fertig. Thank you.